Hello everyone. In this video, I am going to talk about chapter 14, section 14.5, 14.6. In this session, in this video, we're going to learn about concept of conservative forces and determine the potential energy of such forces. And we're going to also apply the principle of conservation energy. Um, A force is said to be conservative if the force done is independent of the path, followed by the force acting on a particle as it moves from A to B. This also means that the work done by the force is in a closed path. For example, from A to B and then go to A, the amount of the amount of work will be zero. So we say the work is conserved. So the work done by a conservative force depends only on the position of the particle, and it's independent of this velocity and acceleration. A more rigorous definition of conservative force makes use of potential function V in the partial differential calculus, as explained here. However, even without the use of these more complicated mathematical relationships, much can be understood and accomplished. The conservative potential energy of a particle system is typically written using the potential function V. There are two major components of V commonly encountered in the mechanical system: the potential energy from gravity and the potential energy from spring or other elastic elements. Potential energy is measure of the amount of work a conservative force will do when a body changes position. In general, for any conservative force system, we can define the potential function V as a function of position, the function done by conservative forces as the particle moves equal to the changing value of the potential. So we have the sum of the gravitational potential energy and the spring potential energy. It is important to become familiar with the two types of potential energy and learn how to calculate their magnitudes. Potential energy due to gravity over here, all you got to do is the total weight multiplied by the height, how much is being elevated. How much is being elevated can be a positive number, it can also be a negative number. For example, if we define the middle line right here as our reference point, our datum, okay, it should be that green line there. Hand sketch is a little off there, but you know what I mean. Right here in the middle is our reference point, is our datum. Anything above it, I have positive potential energy. Anything below this, I have potential energy too, negative potential energy. So another thing is that we can always define our own data. We can define our reference. What we just talk about is in the middle is our where you have zero potential energy. However, if we define the bottom right here as our reference point, as our datum, that means over here you got positive potential energy, over here you got more positive potential energy if you define the bottom as your reference point. Okay, so to keep in mind, it can be positive, it can be negative. Also, datum, we can define our where the datum is. And then elastic potential energy, recall that force of elastic spring is F equals Ks. So the K is the spring constant, S is how much the spring is being stretched or compressed. It's important to realize that the potential energy of a spring, while it looks similar, it is a different formula. The VE, potential energy, potential elastic energy, has a distance s raised to the power or raised to the power second. So we can also write it as VE equals 1/2 Ks squared. So the force is F equals Ks. Uh, um, Spring constant times how much distance is being stretched or compressed. Now the VE, potential elastic energy, will be 1/2 Ks squared. Notice that the potential function VE always yields positive energy. When a particle is acted upon the system of conservative forces, the work done by these forces is conserved and the sum of kinetic energy and potential energy remains constant. In other words, as the particle moves, kinetic energy is converted into potential energy, and potential energy can convert it into kinetic energy as well. This principle is called the principle of conservation of energy, and we write it as T1 plus V1 equals T2 as T2. T1 stands for the kinetic energy of state 1 and its potential energy function for state 1. T1 and T2 represents these energy states as state T. It should be T2 and V2 over here. T2 and V2 represents these energy states as state 2. Recall that the kinetic energy is defined as 1/2 mv squared. Let's take a look at some examples together. We have uh, uh, this color shape for 4 kilogram color. So we have a 4 kilogram C. I was saying this looks like a combination of a straight line and the radius. So this doesn't really have a name shape of pipe. Okay, so at location A, velocity is 2 meters per second. At location A, velocity is 2 meters per second. The spring constant is 400 Newton per meter. The unstretched length of the spring is zero point 0.2 meter. Velocity of the color at B, we're looking for the velocity of color at B. So we are going to write equations. Number one, we are going to write all the total energy that we have at location B. We know that at location B, the spring is being stretched. How much is being stretched? Let me show you here on this slightly bigger diagram. Okay. So when this thing is at B, okay, the total length of this thing, so if you notice that this over here is 0.4 meter. 0.4 meter is the radius of this arc here. Okay, that means from O to A, OA is 0.4 meters. From O to B is 0.4 meters. From O to anywhere in between A to B is all 0.4 meters. Okay, so that's 0.4 here. That means it's 0.4 from OA. OA equals 0.4. And then this portion is 0.1. That means going from O to this portion right here, before we go to the point 1, over here is 0.3. Sorry, OA should be 0.4. I did not write it correctly. So over here, OA is 0.4 because that's the radius of this radius here, radius of this arc here. Okay, so total OA is zero point 0.4. Upper portion from O to the center of that spring is 0.1. That means down here bottom should be 0.3. Okay, I have 0.3 down here. That means, hold on, let me write that correctly. That means also OB from here to here, that's 0.4 as well. OB is 0.4. OA is 0.4, OB is 0.4. Okay, now in this triangle, it's a 3 4 5 triangle. This triangle right here that I'm highlighting, okay, this triangle right here highlighting, you got one side is 0.3. I got the other side, OB, is 0.4, coming from here to here. That means the red part, the hypotenuse, should be 0.5. The hypotenuse should be 0.5 of out of this black triangle I am shading. Okay, this part is 0.5. Okay, so going to the next page, that's where that 0.5 comes from. Now, originally our spring is 0, unstretched length of the spring is 0.2 meter. Going at location B, the length of the spring is 0.5 meter. Okay, so that's what we're doing here. How much is being stretched? 0.5 minus the initial length of the spring, which is 0.5 minus 0.2. Okay, so I have 1/2 times spring constant, which is 400 Newton meter, and then multiply by S squared. That S is how much the spring is being stretched, and then square. Okay, so this portion is the elastic potential energy at location B. And then keep going. I have the gravitational potential energy. Mass is 4. Is it 4? Yeah, 4 kilogram. Okay, mass is 4 kilogram. Multiply by the g, mg, and then times the height. Oh, notice that it's negative 0.4, right? Because I am going down. I am going down. No, I pick on the top where A is, on the top of this shape, the top being the 0. That means at location B is 0.4, negative 0.4 potential energy. So it's negative 4 and m. This is your m, this is your g, and this is your h, and it's negative h because it's below that atom. Okay, That's VB. Kinetic energy at B, we know that velocity is what we're looking for. We're looking for the velocity of a color at B. We don't know the velocity, but we can plug it in. It'll be 1/2 times mass times VB squared. Okay, that square should be on top, should be over here. Okay, so that is the total energy at location B. We can do a similar thing at location A. At location A, the spring is being compressed, right? So spring unstretched is 0.2 meter. Now over here at location A, I got 0.1 meter. So you subtract this two, meaning my spring is being compressed 0.1 meter. So 1/2 times spring constant times the how much spring being compressed square. This gives me the potential elastic energy. And then the TA 1/2 mass times velocity square, that give me the kinetic energy allocation A. Okay, so we know that the velocity at point A is 2 meters per second. So this is the kinetic energy allocation A. So putting that together, I know all the energy together at point B equals all the energy at location A. So putting that together, I can calculate the velocity at location B. There we go. Next problem, we have a roller coaster release from point A, right? We're looking for the minimum height of H so that the car travels around inside the loop at B without leaving the track. Also find the velocity of a car at C down here, at C for this height H of A. Okay, so energy is being conserved, Ta plus not Ta, kinetic energy and potential energy at location A together equals, that's the total energy at A equals your total energy at B. It also equals all your total energy at C as well, energy being conserved, assuming there's no friction. So energy at A, we have 0.5, 1/2 times mass is 800 kilogram given by the problem, 1/2 times mass times velocity square. Release from A, assuming release from A at rest. At A is rest, that means zero velocity at A, so you have 1/2 800 times 0 square. And then multiply, no, addition plus 0, this is the gravitational potential energy being 0. So in other words, I am defining up here as my datum, as my reference point. Anything below this purple line that I drew here, you have potential energy but negative potential energy. Okay, so that's A. And then for B, I have 1/2. I'm using a different color. You have 1/2 800 times velocity b square, 1/2 mass velocity b square, plus the gravitational potential energy at B, which from A to B, the energy, the height difference is in between the purple line and the green line. So H minus 20 is the height that B, how much B is being elevated. Now, when I say elevated, it's negative elevation because the green line where B is below the purple line, below A. Okay, so you have mass, which is 800, G is 9.81, multiplied by the difference in height, H minus 20, which and it's negative because it's below the zero. Using the equation of motion applied at B, so we have normal force, Fn equals man. Okay, and that an is mass times velocity divided by radius of curvature. We've seen this equation before. Using this, I can calculate the v because I know the radius of curvature is 7.5 meter. I can use this to calculate the velocity vb. Okay, velocity vb I know, and then you will be plug in velocity vb here into this equation, and we can calculate unknown. The only unknown is h. Okay, calculate the value h being, hey, we know how much minimum height is needed so that this roller coaster can reach point B at the highest point. Okay, now we know the height, we calculate the height. And then we know that total energy at point C, it's also the same. We can put A and C together. Total energy at A, we talked about this before. Kinetic energy is zero. Potential energy, we set it to be zero as well. At location C, I have 1/2 mass times velocity squared. We don't know that velocity. That's what we're looking for. And then we know the height. From A, we know the potential energy of A is zero. At location C, from the previous stat, we know it's 23.75 below 23.75 below A. Okay, so it's negative potential energy. So mass times gravitational acceleration times this negative height because C is below A. So one equation, one unknown, I can calculate how fast, what's the velocity allocation C. Okay, one last example. I have a spring that can pull that back apparently to launch this ball. Okay, and then we're pulling back the S right here. We pull back the spring 100 millimeter, so or 0.1 meter. Okay, and then we release. When S equal to zero, spring is unstretched. So that means when it's 100 millimeter, that is the length of the spring that's being stretched. Assume all surfaces of the contact to be smooth. Neglect the mass of the spring and the size of the ball. We find the speed of the zero point 0.3 kilogram ball. We know the mass is given to us, and we're looking for the normal reaction of the circular track on the ball when theta equals 60 degrees. We gonna write our principle conservation of energy in conservation of energy equation at location A and B. At location A, you have 1/2 times 0.3 times 0 square. Okay, so that is 1/2 times mass, 0.3 kilogram on the mass of the ball. Okay, so this is your mass, 1/2 mass times velocity. At location A, starting at rest, no kinetic energy, but I have elastic potential energy. How much is that? That will be 1/2 K times S squared. So 1/2 times K is this much, 1500, and then S is zero point 0.1 square. Where's that zero point 0.1 comes from? Remember, it's being stretched by 100 millimeter. We're going to convert it into meter, which is zero point 0.1 square. Okay, so that is TA and VA. At location B, you have 0.1/2 times mass. This, I disagree. It should not be a zero. It should be V square. Over here, it should be a V square. That's a typo. And it's a picture that they inserted into the it's a picture that they inserted here, so I could not update the PowerPoint for you. So it should be 1/2 times mass times V square. Okay, and then the that's your kinetic energy, and then there's also the potential energy, right? Potential energy, we're looking for vertically how much is being elevated. We know that angle is 60 degree, and then over here from the center to here, that's 1.5, and from here to here, okay, I can calculate this portion first using my trig function. That is 1.5 multiply, that is going to be, hold on, let me do that one more time. That is 1.5 cosine 60, this vertical part. That's 1.5 times cosine 60. Okay, right here, if you distributed it in, that is 1.5 times cosine 60. Now total, the radius is 1.5. So you have 1.5 minus 1.5 times cosine 60. This is going to give you the height, how much is being elevated, and how much elevated vertical portions of it from A to B. Not the direct distance from A to B, not the arc from A to B, but vertically how much it's being elevated from location A to location B. So it's 1.5 minus 1.5 cosine 60, and that's what this term is. My potential energy, hold on, let me redo that. It's this portion without, so this is how much it's being elevated. So the mass times zero point 0.3 times this is the M, this is the G, and this is the H, how much H, the change of H from A to B vertical only. Okay. And then This is the kinetic energy at B. This is the gravitational potential energy at B. And then this is the total energy at location A. Put this together, I have one unknown, which is VB. We can solve for the value of VB. And then we're going to draw our free body diagram. You only have two forces, the weight and the normal force. And then I am breaking the kinetic diagram into MAN and MAT, tangent direction and normal direction. The normal direction, you have mvb squared over rho, and then all the normal force, right? And the force on the normal direction, you have the normal force this way, and you have the weight this way and this way. You have the weight, you can break that weight into two different directions, one that's perpendicular to the normal force, one that's tangent to the normal force. And then this tells me that along the normal direction, it's only the cosine 60 portion of the weight. So meaning this portion of the weight. Sorry, let's try it again. We keep on giving me that horizontal line. So only this portion of the weight is along the normal direction. Okay, that is weight W times cosine 60. Right hand side, I know the radius of curvature is 1.5. Radius of from A to B, right? Radius of curvature is 1.5. We know the velocity of B calculated from the previous slide. The only unknown in this equation is your normal force. Okay, we can calculate normal force 8.53. Okay, this is all I want to show you in this video. Hope you find something helpful, and thank you for watching.